Chapter 23, part 2, Lenz law statement. I talked about it in part 1 a little bit, but let's get to more details about it. So the induced EMF resulting from a changing of the magnetic flux has a polarity that leads to induced current whose direction is such that the induced magnetic field opposed to the original flux change. Oh, that was so much of the wording. I don't want to confuse you, so let's go to a very little bit simpler explanation. Nothing likes change. If a magnetic field is changing, the induced current wants to stop the change. So it creates a magnetic field in the opposite direction. Okay, so let's say that I have a loop, okay, and I have a magnetic field, B, that is downward, okay, this is external magnetic field, all right? Now, let's say that this magnetic field is getting stronger and stronger and stronger. So this B is going up, okay? It's getting stronger, so I have an increase in the magnetic field. This will cause the flux to go up, okay? And the flux that's going up will cause the EMF, right? But this EMF is like a source of current, but what is the direction of this current that is happening? The direction of the current that's happening is in the direction that will cause the opposite of the change. So this B is increasing. I should have the current in the direction to oppose to this change, to create a magnetic field that is in the opposite direction of the original magnetic field. In other words, if I want to be in the opposite direction of the magnetic field that is getting stronger, I have the magnetic field to be in this direction, meaning that I have to have a current in this direction to oppose to the change of the original or external magnetic field. Okay. Alternatively, if you imagine to have the same loop in an external magnetic field, okay, B external, but this B that is external is getting weaker and weaker and weaker. So this B is decreasing, and thus this phi or the flux is decreasing, and this will cause an EMF or a source of power in this loop. But where is the direction of the current? The direction of the current is in the direction to oppose the change, to create a magnetic field that do the opposite of the external, that's in the opposite of the external, okay? The opposite of the change in the external. So this B field that is external is getting less and less. It's getting weaker and weaker. So it's getting smaller and smaller. And if I want to oppose to that change, I have to create a magnetic field to help. Okay, so in other words, you have to have a magnetic field in this direction because the external magnetic field is getting weaker and weaker and weaker. So you want to do the opposite. So you want to help. Okay, so you want to have the magnetic field in the direction to oppose to that change. Okay, so you have to be in this direction. In other words, you have to have a current in this direction to oppose to that change. Okay, so the induced, now let's do some strategy. I just explained it, but let's go over that, over this three things one more time. So determine whether the magnetic flux that penetrates the coil is increasing or decreasing. Okay, in our case here, the first one was increasing, second one was decreasing. 2, find what direction of the induced magnetic field must be so that it can oppose the change in the flux by adding or subtracting from the original field. For example, here the flux was increasing, so I put the magnetic field in the opposite direction to oppose to that increasing flux. And here, in the second example, the flux was decreasing, So I put the B field in the direction to oppose to that decreasing flux. So they should be in the same direction. And 3, use the right-hand rule to determine the direction of the induced current. And that's what we did. So EMF produced by a moving magnet. We talked about it in part 1 a little bit. So let's go over it one more time. I have a magnetic, I have a bar magnet here. South pole is here, north pole is right there. And this is getting closer to this loop, okay? When this gets closer to the loop, I have all of these magnetic field lines. Uh-oh, let me, okay, I fixed it. Now, so this magnetic bar or this bar magnet is getting close to this loop. So this B field lines are getting stronger because I'm getting closer. So I have a B field in this direction, and this B field is getting stronger. So this B field is going up, getting stronger. This means that the flux is going up. Number of B lines or number of magnetic lines going through this field or this area is getting up or increasing. So that's the flux is increasing, okay? And so I should have the induced current in the direction to oppose to this change. In other words, I have to have the induced magnetic field in the opposite direction, okay? So I have to have the current in this direction to create this B field that I want, okay? A permanent magnet is approaching to the loop of wire. The external circuit consists of a resistor, which you can see there. Find the direction of the induced current and the polarity of the induced EMF. So here, as the magnet moves towards the loop, the magnetic flux increases, as I just talked about it. So this flux is increasing. So phi is getting a higher value. It's going up because B is increasing, okay? Because the magnetic field is increasing. Therefore, the induced current must create a magnetic field in the opposite direction in order to create a magnetic field to the left. The opposite terminal in the left and a negative terminal in the right. So this should be positive, this should be negative in order to have a current in this direction. So you have the current going somehow counterclockwise to create a magnetic field to the left. The current flow from the positive terminal to the of the resistors through the negative terminal or counterclockwise. Let's take a look at this example. Or lecture question number 5. And let me see if I can make this a little bit bigger. Okay, so here we go. The EMF produces by the moving copper ring. So I have a copper ring here going all the way from point 1 to point 5. And this, on its path, it will go through an external magnetic field, okay? It will go through an external magnetic field. Now at point 1 here, there is no flux going through it because if you remember, flux was B dot A, or it was B A cosine of theta. Okay, so there is point 1, there is no B, so B is 0. So the flux is 0 at point 1. At point 2, right there, okay, the number of lines is getting stronger and stronger. Number of lines are increasing because this ring is going in. So you'll have, by time, you'll have more lines going through this ring, okay? And these are, the lines are going inside, so you have to have your current in a direction to oppose to that. In other words, you have to have your current in a counterclockwise direction to create a field outside of the page. So the B should be outside of the page, okay, out, in order to oppose to that. At point C, there is no EMF because there is no change of the flux. The flux is the same, so phi is the same. Point 4, right there, the number of lines are getting smaller and smaller. So the flux is decreasing. As the flux decreases, the B field is decreases. So you have to have your current in the direction to oppose to that. Okay, so one more time. At point 4, the number of B field or the number of magnetic field lines are decreasing. Okay, this caused the decrease in the flux. So you have to have your current in the direction to oppose to that. In other words, you have to be in the same direction to help. So you have to have your current in the clockwise direction to create a B field inside the page. Okay, so this will cause a B field that is going inside the page. Okay, and at point 5, there is no B field, or phi is 0. So let's take a look at this question. A wire loop is being pulled through a uniform magnetic field. Okay, what is the direction of the induced current? So do we have any change in the flux? No. Do we have any change in the magnetic field? No. So because this is already inside a magnetic field, there is no current at all. This is exactly like point 3 in our previous problem. So the answer is no induced current. However, if you're looking at the next question, a wire loop is being pulled through a uniform magnetic field that suddenly ends, so right at the edge, right here. What's the direction of the induced current? So when you're looking at this, the number of B lines, or the number of magnetic lines, is decreasing, okay, that are going through this loop. This means that you have less flux going through, less number of lines going through this loop, and this will cause the change of the flux, right? So that means you will have an EMF. You have an electromotive force. This electromotive force is, and if you remember what the formula was, that was the formula. This electromotive force is causing a current. But what is the direction of that current? The direction of the current is in the direction to do the opposite thing. The B field is decreasing, so you have to have the current in the direction to do the opposite action. In other words, since this B is decreasing, it's getting smaller, you have to be in a direction to oppose to that change, okay? So in other words, you have to be in this direction to help, because this is decreasing. So you have to increase the your current should be in the direction to increase it, okay? To increase the already decreased magnetic field, okay? So that's why this B is decreasing. So you have to have a B that is coming from EMF, okay, going inside, and do the opposite. I refer you one more time to this 3 reasoning strategy. Determine whether the magnetic flux that penetrates the coil is increasing or decreasing. Find what the direction of the induced magnetic field must be so that it can oppose to the change in the flux by adding or subtracting from the original field. And then use the right-hand rule to determine the current. If that's the case, now let's take a look at another example. If a coil is shrinking in a magnetic field pointing into the page, so in other words, the area is getting smaller, okay? So that means that the flux is getting smaller because flux was B dot A, okay? So that means that the flux is getting smaller. If flux is getting smaller, then I have to have a current inside this loop in a way to do the opposite thing. In other words, I have to have the current in a way to do the opposite action. In other words, since this flux is decreasing, I have to increase the flux, okay? And the B field is inside the page, so I have to have the current in this direction. Because based on right-hand rule, then if you have current in this direction, this will cause a B field to go inside. Okay, this will cause a B field to go inside. So this means it will be clockwise. Lenz law and induced current. So this conducting rod completes the circuit. So you have a complete circuit right here, okay? As it falls, the magnetic flux decreases and the current is induced. So let's take a look. What we have here is this, that I have a magnetic field lines that are coming out of the page. So this is out of the page. Okay. And this area is getting smaller. If the area is getting smaller, then your flux is getting smaller. Okay. If your flux is getting smaller, you have to have your current in a direction to oppose to this decreasing flux. Okay. You have to have your current or the induced current in the direction to oppose to this decreasing flux. In other words, this is out of the page. In order to oppose to this decreasing flux, you have to have the current in this direction. To oppose to this, okay? So the current wants to keep the flux constant, therefore the induced current will be in a direction such as to add to the magnetic field and flux. The force due to the current to the left and to the magnetic field out of the page is upward. So in other words, you have a rod with a current to the left, so this is the current. Put your 4 fingers in the direction of the current. B is coming out of your palm or out of your hand, and then your thumb should show the direction of the force. So in other words, you have to have something like this. 4 fingers in the direction of current. B is coming out of your hand, and then your thumb should show the direction of force, which in this case is upward. Okay. We have something called eddy current, and this current is happening in a sheet of metal. Currents can also flow in bulk. Conductors, as you can see here, as I said, sheet of metal. These induce currents called eddy currents and can be, powerful brakes. So as you can see that we have a force up towards the top, okay? And then these are the eddy currents that are happening inside a sheet of metal. So finding the induced EMF. So this diagram shows the variable we need to calculate in the problems or, in induced EMF questions. So what I have is that I have a rod, and this rod is moving with the velocity v. So this is moving with the velocity v. All right. So after time delta t, it has moved this much, which I'm just going to call it delta x. Okay. And the change of the area from this point to this point is delta A. So this will cause the area to change. So the area is changing. The area is increasing. This means that the flux, which was V dot A, is increasing, okay? And if flux is increasing, you have to have your magnetic field in a direction to oppose this increasing flux. In other words, you have to have your magnetic field to go inside the page because the original magnetic field was outside. So you have to have your magnetic field to go inside to oppose to that change of the flux, okay? So this means that your current should be in the clockwise direction. So current should be in clockwise direction. Okay, so with all of that having said, and having the length of this rod being L, let's take a look at the EMF. So remember, phi was B dot A, flux was B dot A, which is B A cosine of theta, okay? And then so if you consider that, and let's say that this cosine of theta is just 1, okay? Then your phi, or delta phi, is B delta A, okay? And so delta phi is B, delta A is this area, okay? So one side times the other. Which means L times delta X, which is BL delta X was V delta T, right? And if you put this B VL delta T, which is right here, and putting it right here for the equation of the EMF, then you'll have BVL delta T over delta T, and number of turns, let's just say it's a loop with one turn. So this delta T and delta T will cancel out, and we'll have BVL. And this is what we used back in one of our examples. I think it was one of the examples, example number 3, if I'm not mistaken. Right here. VBL, right? And we have it right here as well. This is what we have done, BVL, okay? And once you have that, this is the EMF, B, which is the magnetic field. B is the velocity of the rod, and L is the length of the rod, because this delta T and delta T cancel out, okay? Is this and this has cancel out. And so you're left with that. Once you have that, so you have the B field, and you have a rod moving, you can find the electric field. The electric field is just B times the velocity. So if I ask you in this type of questions what the E field or electric field is, you have to be able to calculate that, because you have the velocity and the magnetic field. So if the rod is to move at the constant speed, the external force must be exerted on it. This force should have equal magnitude and in the opposite direction of the magnetic force. So if you're looking at this, there is a force. So there is a current inside this rod. Using the right hand rule, put your 4 fingers in the direction of the current. B is coming out of the page, okay? So it should come out of your palm, and this force is showing you your thumb. So your thumb will be in this direction. And if you want, so there is a constant force putting this rod back to its original place. So if you want this rod to move with the constant speed, you have to apply an external force with the same magnitude to the rod in the opposite direction. Okay, so if the rod is to move at the constant speed, okay, so it means there is no external force acting on it. An external force must be exerted on it in the opposite direction of the magnetic force. So if this was our rod, this was the direction of the magnetic here we go. Okay, and then so there is a constant magnetic force because there is a current inside this wire. So there has to be a magnetic, an external force in the opposite direction, F of external. Okay, So mechanical power, the mechanical power delivered by the external force is F times V, and we have remember this from our physics 1, but if you don't, I can real quick look show you how I have done it. So remember that P was W over T, okay, and this W was work, so it was F dot D, okay, and it is FD cosine theta. This is the dot product between them. And T is just time. And so this distance over time is the velocity, isn't it? So this is the velocity, which means that the power is F dot V. So you can see right there. Okay, so we know what the F is. This is the force, right? It is right here. B squared VL squared over R. How did we derive this? I think I forgot to explain it. So F is I dot L cross B, okay? Or in this case, since they're all in the perpendicular to one another, it is ILV, okay? And instead of this I can use V over R. So I is V over R, or EMF over R, okay? So this EMF is BVL, okay? So BVL over R, and I can substitute that right here. Once I do that, I'll have something like this, which I can reduce it and write it like B squared VL squared over R. So B squared VL squared over R times V. So V and V will be B squared V squared L squared over R. Okay? So this is the mechanical power. If you compare that to the electric power, which is Ri squared, for I have BVL over R squared, and for R is R, and then I'll have B squared V squared L squared over R. So essentially they are the same. Okay, they are the same, which means the mechanical power has to be converted directly to the electric power. All right, so this is exactly what we have seen in an electrical engine. One more time, the mechanical power has been converted directly into the electrical power because they are the same value. This is exactly what we see in electric generators. Okay, so the electric generators converts mechanical energy into electric energy. How much are they? What the power is? This is the power. So let's see how they work. So we have an outside source of energy is used to turn the coil. So we have a mechanical input. This will cause this coil to move with the frequency of omega. Okay. Now, the B field is the same because B is coming from this magnet. The area for this coil is the same, but what's changing here is the angle between them. Remember what the flux was? Flux was B dot A, which was BA cosine theta. B is constant, A is constant, but the cosine of the angle between them is constantly changing because this is rotating. So this cosine, this theta is changing. This means the flux is changing. When the flux is changing, we have an EMF, okay, which is negative N delta phi over delta T, okay? And this will cause a current to go through this loop or this part of the circuit, and this can be used to to light bulb to start burning, or for any electrical output. All right, so induced EMF, as I was just talking about, is since that omega, or since that theta is changing, then E can be right in this way. So if I want to write it down, I will have the value for E, or EMF, is negative, is N delta phi over delta T. If this is happening in a very short amount of time, delta can be replaced with D, okay? And N, D, what phi is, BA cosine theta over dt, okay? And then B is constant, A is constant, so they can come out of this derivative. So NBA, d of the cosine theta over dt. And this theta is omega t, by the way. This is what we learned in physics 1, because omega was angular velocity, was delta theta over delta t, or theta over t. So I can just replace that with this, N BA d of the cosine of omega t over dt. This means that I have to take a derivative with respect to t from cosine omega t, okay? And this is what we have right here. If you take one derivative, then let me actually put this in a box. Then your E is NBA, derivative of cosine omega t with respect to t will give you omega is outside and sine omega t. So this will be your EMF. So this will be that. Okay. Electric motors. An electric motor is exactly the same, but doing in the opposite of generators, okay? So remember the generator, you had a mechanical input to generate something or electrical output, but the electric motors are exactly in the opposite, are doing exactly opposite of the generators. So it used the torque on the current loop to create mechanical energy. So in other words, you have an electric input. This electric input will go through this loop and causes a force here and a force here. And this means that this loop will start rotating clockwise, which means that I have a mechanical output. So what I have here is that I have an electrical input. This is an AC source, okay, that has a change of the current. Because the current is changing, so the B field is changing, so there will be a force, okay, and then this will cause the rotation of this shaft, which causes mechanical output. But let's talk about this force for a second. You have a current that is going in this direction, okay, which means that you have 4 fingers in the direction of the current. B is coming out of your hand, okay, out of your palm, and your thumb should show the direction of the force, which is upward. So for this part, you have an upward force, and for this part, you have a downward force, which means that this will do a clockwise rotation, okay? So this will do a clockwise rotation. Now, this will cause something called back EMF. So the back EMF generated inside the electric motors. When a motor is operating, 2 sources of EMFs are present. the applied EMF, V, that provides current to drive the motor, okay, which is right here, and the EMF induced by the generator, like acting in a rotating coil, because you have a rotating coil inside a magnetic field, there will be a back EMF in the opposite direction, okay? One more time. The EMF induced by the generator, like acting on the of the rotating coil, okay, so which is called back EMF. And if you want to find the current, that's the actual EMF that's being applied, which is V, minus the back EMF. So this E is back EMF, okay? This is the actual EMF. This is the resistor, and this will be the current. So let's take a look at this example. The coil of an AC motor has a resistance of 4.1 ohms. So we know what R is, which is 4.1. And it's plugged into the outlet where the voltage is 120 volts. So we know what the voltage is, which is 120. So that's the input inside the coil. And the coil developed a back EMF of 118 volts. So E is 118 volts. When rotating at a normal speed, the motor is turning a wheel, and this is what we have seen. So this is exactly what you can see in electric motors, okay? So, A, find the current when the motor first start up. So when the motor first start up, it did not have any back EMF or anything, okay? So in other words, for A, I is V over R, and there is no EMF at the beginning, okay, which is 120 over 4.1, which will give us 29.3. Okay, so this is the current that's going at the beginning. But then B, the current when the motor is operating at normal speed. At that point, you have enough back EMF. So you have to have V minus E over R. So you have 120 minus 118, 118 over 4.1, which then this will be 0.49 amp. So mutual inductance, a changing current in the primary coil creates a changing of the magnetic flux through the secondary coil, which leads to the induced EMF in the secondary coil. So let's see what's happening. We have an AC generator, and this will go in a primary coil, okay? So this AC generator, this is alternative current. So this I is changing. When I is changing, remember what the B was for a solenoid or for the coil? Mu 0 Ni from previous chapter, right? So if that's the case, when I is changing, then B is changing, okay? So when this I is changing, then this B is changing. And if that's the case, this B is changing, so the flux inside the secondary coil is changing. And that will cause a, current inside the secondary circuit. As you can see, the current is not zero. Changing of the magnetic field lines produced by a primary coil will produce a secondary current, a current inside a secondary coil. This effect is called mutual induction. A change in one coil or one solenoid will cause change of the current in the secondary one. Now, remember this formula, E equals negative N delta phi over delta T. For the mutual inductions, okay, we'll have E being negative M delta I over delta T. This M is mutual inductance, okay? And for example, if you have two solenoids, then this M would be mu 0, number of turns in the first one, number of turns in the second one. The area, which we assume there it's the same for both of them, it could be different, over L, the length. Okay, so this is called mutual inductance. And it has a unit, SI units of Henry, and 1 Henry is 1 volts times seconds over amp or area. If you want to find the EMF due to this mutual inductance, that's the formula for it, negative M, mutual inductance. This is usually be given to you. Delta I, change of the current over delta T. Okay, so the effect in which the changing current in a circuit induce an EMF in the same circuit is referred to self-inductance. One more time. If I have an AC generator that is causing a current going through this coil, but this current is changing. This current is changing. This will cause the B to change. So then because this B is changing, this coil is reacting to that change. Based on the Lenz law, there will be a current induced inside this coil or inside this circuit that is called self-induction, or it will be in the opposite direction of this change. Okay, so let's say that I have a B field. Let's actually look at this example. Let's say that I have a current going through this solenoid, okay, and then this current is decreasing. This means the B is decreasing. This means the flux is decreasing, right? Everything is decreasing. So the there will be a self-induction inside this coil, which will do the opposite, which will oppose to this change. This means that it will be in the same direction. This will be in the same direction. So this means that I will have a current inside these in the way to oppose to this change. The change, what was the change? The change was reducing the current, reducing the B field, reducing the flux. Everything is getting reduced. So I have to have an induced current inside this coil in the direction or in a way to oppose to this change, which means that it has to be in this direction to go in the same direction of the B field that's already getting decreased, to help it, to oppose the change, okay? Remember, I talked about the strategy that you need to have. Find the direction of the induced magnetic field must be so that it can oppose to the change in the flux by adding or subtracting from the original field. So it has to add at this. It has to, in this case, it has to be in the direction to add to the original B field because the original B field is decreasing. So it has to be in a direction to oppose to that change. So it has to be in the same direction. So self-inductance equation, if you want to find the EMF of that. So this is the EMF is negative L delta I over delta T. This L is self-inductance. It has a formula, which we'll talk about it. And this I unit is, again, Henry. So the energy is stored in an inductor. Energy is stored in an inductor. The energy is half Li squared, and this L is the inductance, which has a value associated with it, usually be given to you. And the energy density is, this is something that Your book has shown how to drive it. I don't want you to, I don't want to spend time and show you what, how to derive this equation, but just energy density is V squared over 2 mu 0. So, transformers and its equations. A transformer is a device for increasing or decreasing an AC voltage. Okay, so so I have an AC generator going to this primary coil, and then I have a magnetic field lines going through this iron coil because of existence of this primary coil. And the number of turns between primary coil and the secondary coil are different. And the secondary coil has a different number of turns. Okay, and then this secondary coil, because of existence of this B field inside this iron core, it will induce, this B field will induce a current inside the secondary coil. And you can see, for example, this will be your TV, for example. Now, this the primary coil has an EMF of negative NFP delta phi over delta T. The secondary coil will have an EMF of negative NFS delta phi over delta T. And if you divide them, you will end up having the ratio of the EMF of a secondary to the ratio of the EMF of the primary is just essentially the ratio of their number of turns. Okay? And if you compare the voltages, the VF secondary over the VF primary is again, because this is exactly the EMF. So this is the EMF of the secondary. This is the EMF of the primary. Okay? This is exactly the value of the ratio of the number of turns. Now, if you want to compare their currents, they have in the opposite relationship. So IFS over IFP is VFP over VFS. In other words, a transformer that stepped up the voltage simultaneously steps down the current. So if voltage is up, the current is down. Okay? And a transformer that steps down the voltage steps up the current. Okay? So and this is the end of our chapter 23. So how the electricity gets to your home. You have a power plant that creates this electricity. This will go to a transformer and getting up. So stepping up, going to a higher voltage. So for example, here, the voltage here is 240,000 volts. And then this will go, this very high voltage will go through these transmission lines. And then this will go to a step down transformer. Okay. This is exactly what I was talking about, a step down transformer, and gets to a lower voltage but higher current. Okay. Which means that eventually once it gets to your home, it's about 120 volts. Or in this case, 240 volts. Okay. The point is that you have transformers transforming this voltage for you based on the resistance and the current. So let's take a look at a summary of chapter 23. A changing of a magnetic field can induce a current in the circuit. The magnitude and of the induced current depends on the rate of the change of the magnetic field. Okay, so the flux was B dot A, and I can write it as BA cosine of theta. If BA over theta is changing, then the flux is changing. The change of the flux can induce a EMF. Okay. Now, this induced EMF, if you have a rod moving in the B field, then induced EMF is BVL. B is the external magnetic field, V is the velocity of the rod, and L is the length of the rod. Okay. And the EMF produced by a generator is NBA omega sine omega t. I have shown you here what it means and how to derive it. Let's see where it was. maybe here. Yeah. So NBA omega sine omega t. And the electric motor is basically a generator operated in reverse. One will turn the electric to mechanical, and the other one will turn the mechanical energy to electric energy. Inductance occurs when a coil with a changing current induces an EMF in itself. Okay. And definition of inductance, you have EMF being equal to L delta I over delta T. And then the inductance of a solenoid is, so this value, if you have a solenoid for the inductance, this L for the solenoid is mu 0 ns squared AL. Mu 0 ns squared is just capital N over L. And then this L will cancel out, so you have mu 0 ns squared over L times A. And then for RL circuits, meaning that if you have a resistance and a solenoid, or L, inside your circuit, there is a time constant, which we showed what by R, by tau, which is L over R. So tau is L over R, and this is the inductance, which is right here. Why is it important? Because some of the characteristics of this RL circuits are related to that tau. For example, the current is that EMF over R, 1 minus e to the power of negative t over tau. Okay, so we can just put for tau L over R, or what we have here. One of the most important things is at the beginning, if t is 0, then I is 0, okay? And if t goes to infinity, means for a very long time, okay, then your I is just V over R, or EMF over R. And so there will be a magnetic energy density, which I just talked about a few minutes ago, B squared over 2 mu 0, and then transformers equations. I of S over I of P, the most important one was V of P over V of S, or NFP over N of S. We know what this part was. NFP over N of S is directly proportional to the EMF of P, or the primary coil to the secondary coil, but then this is reversely proportional to their currents. It means if you have a small voltage, then you have a high current, and this is exactly what's happening once we want to get voltage from the power plants to our house. Okay, if you have a high or a low voltage, then you have a high current. Okay, this is the end of chapter 23. Let me know if you have any questions. I would encourage you to go and read, to watch this video a couple times at least. These are very complicated and important subjects. It could be really time-consuming to learn, and it could be really confusing. So I want you to go over these, problem solve in this chapter, and the examples that I solve here, and overall the concepts couple times until you master it. Okay, let me know if you have any questions.